Hello everyone, this is Wang Jiazhang from Hong Kong University of Science and Technology. It's an honor to present our work, Noise2Info, Noisy Image to Informational Noise for Self-Supervised Image Denoising. First, I will introduce the motivation of this work. Image denoising is important in many scenarios, such as photo sharing on social media, medical image denoising, radar image repairing, etc. In recent years, traditional methods for image denoising are quickly surpassed by supervised deep learning methods, which use clean images to update models. However, clean images are hardly available in real-world applications. With only noisy images, self-supervised deep learning models are proposed. And clean images are not available. Directly using noisy images and guidance will push the model to learn an identical function. To be more specific, the model input includes X, minimizing the loss of model output, and X will directly learn an output equal to X. The solution is to learn each pixel as under G invariant. We can input into subsets, then we recover Gi only based on its complementary set. The model input excludes X, so we can simply minimize the loss of output and X. F can never learn an identical function. However, this method only uses complements, where information from the pixel itself is wasted. To avoid the model learning an identical function, we minimize a special loss that leverages both external and internal information. The proposed loss function can be written as follows, which is composed of internal and external loss with the standard deviation of the noise. However, in real-world applications, the sigma is still unknown. This motivates us to design a totally self-supervised method considering both internal and external information. We derive sigma-related information only using the noisy images. Here is the problem formulation. We define the noisy images as X and the clean images as Y. The noise map underlying Y is denoted as N. Supervised learning minimizes a loss between denoising output Fx and the clean image Y. Self-supervised learning is proposed to first recover pixels using their complements, but model F only considers external information, and we want to train models F to consider internal information. The existing method transforms the minimization of supervised loss into an upper bound, which requires noisy images and the unknown standard deviation of noise. This leads to our problem: how to estimate sigma only based on noisy images so that the method is end-to-end self-supervised. Here are the algorithms. We first give a preliminary upper bound of sigma n, where clean image Y is still intractable. Then we transfer the tractable term into the L2 norm of real noise and remove noise from our model. The distribution of real noise is still unknown. To get a lower bound, we use the MLE of removed noises to replace it. Now we can use the MLE for sampling. The derived MLE is shown in the following lemma. It is unknown how the sampled pixels are matched with the removed noises. We derive its lower bound instead. If the model is better, the lower bound is tighter. We further propose a theorem for derived bound. For details and proof, please check the paper. Finally, using the estimation, we propose an algorithm, Noise2Info, which simultaneously extracts information of noise and updates the noisy model. Finally, we illustrate the performance. In the experiments, we use 3 benchmark datasets widely used in self-supervised denoising. We also conduct experiments on real-world datasets and synthetic datasets. For comparison, we have 2 traditional algorithms without learning, where 2 supervised methods and 4 self-supervised methods are compared. Here we show the performance of different algorithms on 3 benchmarks. The matrix is PSNR, which is the larger the better. Our model outperforms other methods. We also conduct experiments for generality. 3 datasets out of our assumptions are tested. our Noise2Info outperforms other methods. Here we show the estimation of sigma n. Our estimation closely upper bounds the real one. Besides, the estimation is more accurate during training, which validates our proposition. Thank you for your attention. Here are the open source code and datasets.